choice answers for the chapter on sound that involves Doppler effect, beats, and intensity, and other topics. Question 1 is a direct one. I just let it run by. Two people are talking at a distance of 3 meters from where you are, and you measure the sound intensity as 1.1 times 10 to the negative 7 watt per meter squared. Another student is 4 meters away from the talkers. What sound intensity does the other student measure? Now, as you can see, intensity is inversely proportional to the square of the distance. So I1 by I2 is R2 squared by R1 squared. And then we are asked to find I2, so we know I1 and the other two distances. This is 3 squared and this is 4 squared, of course, and you get I2 as 6.2 times 10 to the negative 8 watt meter raised to minus 2. In the second one, you are driving along a highway at 25 meters per second when you hear the siren of an emergency vehicle that is traveling in the opposite direction on the other side of the highway. When it's approaching you, you hear the frequency as 2300, but when it's past you, the frequency becomes 1600. What is the speed of the vehicle? The speed of sound in air is 343 meters per second. Here you have two different situations. In the first instance, the source of sound is coming towards you, and therefore the frequency is going to appear to have gone up, right? All right. So the formula is F prime is F V plus L times or divided by V minus Vs. How do we know? Because the frequency F prime should be greater than F, and therefore the numerator should have gone up, the denominator should have gone down. So plug it into that. You do not know the original frequency. You're looking for the velocity of the source. In the second case, the source is going away from the listener. Therefore, the frequency would appear to have gone down. And so you see that in the numerator you have a negative, and the denominator you have a positive. So that's the difference, and when you plug it in, you have two equations now. Let me call them 1 and 2. And if you divide 1 by 2, well, you may also solve this in other ways, but if you divide this is what you get. On the left side, you just divided 2300 by 1600. On the right side, you know that this is going to flip, so that's why you have 318, which which is 343 minus 25, and 368 is 343 plus 25. Now 2300 divided by 1600 comes out to be 1.4375. And 368 divided by 318 is 1.16. So you get 368 divided by 318 is 1.16. Now I can distribute the terms, and you get 493. This is just cross multiplying and distributing the terms. And then bring the terms that have Vs onto one side, and you get the answer as 36.6 meters per second. In the third one, a boy on a bicycle approaches a brick wall as he sounds his horn at a frequency of 400 Hz. The sound he hears reflected back is at a frequency 408 hertz. At what speed is the boy riding his bicycle toward the wall? Assume that the speed of sound in air is 340 meters per second. Here again, you could treat this as two different instances. One, when the sound is going from his horn to the wall, and the second, when it's reflected off the wall and coming to him. Alright, that's the boy, the bicycle, the sound moving towards the wall, and of course in this case the wall is at rest. So in the first case, you assume that the wall is the listener, and surely the frequency would appear to have increased. Why? Because the source is moving towards. Therefore, in the denominator, you have V minus Vs. Remember that when it approaches, when the source comes towards you, the frequency appears to go up, and when it goes away from you, it appears to have gone down. In the second case, okay, that was a mistake there, because in the second case, the sound is reflected off the walls and coming to him. So the source of sound is now at rest while the listener is moving. And another thing is that now again the frequency would appear to go up. And so in the numerator now you are going to have plus, you're going to have addition right there. And another important thing is that the apparent frequency from the first case is what you take as the original frequency. So that means the frequency has gone up from F to F prime, and then from F prime to F double prime. You see that? Okay. So now 400 times 340. It's just a matter of substituting for F prime. So I've substituted this whole thing for F prime, as you can see. There it is. Then times 340 plus Bs by 340. All right. The 340s get cancelled. And you just have to solve this equation carefully to get the velocity of the source is 3.37 meter per second. In this question, the speed of sound through the ground is about 6 kilometers per second, while the speed of sound in air is 343 meters per second. A very powerful explosion occurs some distance away, and you feel the ground vibrate 60 seconds before you hear the sound of the explosion. How far away is the explosion? Now, the 60 seconds that is given is the time difference between you hearing the sound through the air and the sound or the vibrations coming through the ground. Because obviously the vibrations through the ground get to you much faster because the speed is 6,000 meters per second. So it's the time difference. Therefore we set up an equation for time difference, and time difference is, time is distance divided by speed, and therefore the time through air minus the time through the ground is delta t. And when you do 1 divided by 343, you get this number, and 1 divided by 6,000 is the small number. So this is just math. Now d is common, so take the difference between these two terms. You get that. That's equal to 60, and therefore d is 60 divided by this number, which gives you 21,834 meters, which is 21.83 kilometers. In the fifth question, a car horn emits a frequency of 400 hertz. A car traveling at 20 meters per second sounds the horn as it approaches a stationary pedestrian. What frequency does the pedestrian hear? Speed of sound is 343 meters per second. Here, the frequency is going to appear to have increased, and the listener is at rest. There is the listener at rest. And so, we know that in the denominator, it has to be a minus because we know that the frequency would appear to increase. Now, that's the whole formula, but you know that the listener is at rest, so that term becomes 0, and here you have a minus. That is 343 minus 20. That's why you have 323. Although I have not written it. Okay, so this is 343 minus 20. That's why you have 323, and you get 424.76 hertz. In the sixth one, as you stand by the side of the road, a car approaches you at a constant speed. So it's approaching you, that means the frequency would appear to go up. And you hear a frequency of 80 hertz. After the car passes by or goes by, you hear a frequency of 60 hertz. What is the speed of the car? Alright, so this is similar to one that we did before. Approaching, 80 is f times 343 by minus now in the denominator, correct? And when it's receding, which means going away, 60 is f 343 by 343 plus Vs. You have those two equations, divide one by the other. The frequencies will get cancelled right there when you divide. And now all you got to do is cross multiply and solve this equation. 8 times 343, you get this number, and then 8 times Vs. Similarly, 343 times 6 is this one, and then 6 Vs, which is plus. Okay, obviously I put 1 0 because I'd forgotten that I'd cancelled out the zeros. That's why I had to remove those 2 zeros from there. And 14 Vs is 6860. Therefore, the source is moving at 49 meters per second. In the seventh one, a bat emits a sound at frequency of 30 kilohertz as it approaches a wall. The bat detects beats such that the frequency of the echo is 900 hertz higher than the frequency the bat is emitting. What is the speed of the bat? Okay, the speed of sound in air is 340 meters per second. Here again, 2 instances as we did before, because the sound gets reflected from the wall. As you can see, first case, the listener is at rest and the frequency would appear to have increased, so the denominator has a negative. Second case, the wall becomes the source and it's at rest. And again, the frequency would appear to have increased. Therefore, the numerator has a plus. And when you take the difference between these, f2 prime minus f prime, okay, hold on. It's f2 prime minus, okay, that's right, because I've already substituted for f prime here. You see this whole thing has been substituted here. Okay. I've just taken out the frequency from here. And I'm just multiplying this here because when you take the LCM, that's what you do. You solve it in your own way because there's only one unknown quantity, which is velocity of the source now. And here I'm cross multiplying, and sure enough, there is some math that you got to do really carefully. And you would get the velocity of the source as 5.02 meters per second. So that is the answer, 5 meters per second. In the eighth question, you are driving along a highway at 35 meters per second. When you hear the siren of a police car approaching you from behind, and you perceive the frequency as 1470 hertz. You're relieved that he's in pursuit of a different speed when he continues past you, but now you perceive the frequency to be 1400 hertz. What's the frequency of the siren in the police car? The speed of sound is 343 meters per second. All right, as the police car is approaching you, the frequency appears to have increased. And when it's going away from you, it appears to have decreased. So these are the equations in the numerator. This is because, you have both minus because you are going away. Now, your going away tends to decrease the apparent frequency. That's why you have negative here. But the source approaching you tends to make it higher. That's why the denominator is negative. Okay. And the second case, that was given as 35. In the second case, frequency goes down, therefore it's positive in the numerator and the denominator. Because you moving towards the police car tends to keep it lower. When you move, the listener moving tends to increase and the source moving tends to decrease. There's quite a bit of understanding that is there. In short, if the source is coming towards the listener or the listener is going towards the source, the frequency apparently goes up. So you have to keep that concept in your mind while you work out Doppler effect. And there are no shortcuts. Now, as I was speaking, you see, it's all math after that you have to figure out, that you have to do really carefully. Some big numbers, because I'm distributing this, multiply these two, you get this number, and multiply that. And, same thing in the denominator. And finally, when you solve, you get 43.33 meters per second. And from there, you can put that, because what we got is the velocity of the source, and substitute that back and find the frequency as 1430 hertz. Let me take you back and show you that what we did get was the velocity of the source. And so we put that back into the equation and get the frequency, the actual frequency, which is 1430 hertz. Ninth one is about an open, no, it's a closed pipe, because it's open at one end and closed at the other, and the fundamental frequency is given. What's the speed of sound in this gas? Nothing can be easier than this. Just have to remember that if it's an open pipe, I'm just doing this, just to show you the difference. If it was an open pipe, then the speed would have been 240 meter per second. But in this case, it's a closed pipe, so the fundamental formula is V by 4 times the length, and the speed is 480. Again, I'm writing hertz, meter per second. Now, that's the only answer. That's the part that is the answer to this problem. This is just done for comparison's sake, if it was an open pipe. All right, and the last one, the intensity level of a power mower at a distance of 1 meter is 100 decibels. You wake up one morning to find that 4 of your neighbors, too bad, are mowing the lawn 20 meters from your open bedroom window. Now, notice that both the distance and the number of lawn mowers have changed. So, this is the intensity formula, 10 log I by I naught, where I naught is always 10 to the negative 12. So from the first case, it was 100 decibels. We're trying to change it into conventional units. And instead of log, you can write 10 to the power 10, because this this number here is 10, so 10 to the power 10 here, and you need not write log there. So I is 0.01 watt per meter squared. Now consider the distance factor, and it's an inverse ratio, as you can see. And the distances are 1 meter and 20 meters. So you end up with 1 by 400, because 20 squared is 400. So now the effective intensity is really 2.5 times 10 to the negative 5. But you have 4 of them. So you multiply this with 4. And you get 10 times 10 to the negative 5. And now convert it back into decibels using the formula. And you get 80 decibels. And so that is what it is. These are the answers, and hopefully you've taken time to go through this and understand this, and then do good on the exam that is right there at the door 2 days from now. Thank you.